Welcome to the Deep Dive. This is where we sort through stacks of research articles, notes, you name it, to really pull out the insights that matter for you. Today we're diving into building materials. This actually came from a listener who asked about wood, why we use it so much, where it falls short, and crucially what the alternatives are, especially if you're building somewhere that faces, well, serious weather challenges. So our mission here is to pull out the core takeaways. We'll look at why wood's been the go-to for so long, pinpoint its weaknesses in extreme conditions, and then explore what really goes into making a home stand up to the worst. You'll get a solid understanding of, what works and why.
And this is really relevant right now, isn't it, with all the focus on the environment. And let's face it, the increase in extreme weather, we're not just talking about what materials to use, but really why these choices are so important for you, for your safety, and even your wallet.
Okay, let's kick things off then with wood. The sources really dig into why it's still such a popular choice for houses today. And it's way more than just sticking with tradition, right?
Oh, absolutely. I mean, one of the most fascinating things is that wood is pretty much the only major structural building material that's actually renewable.
Renewable. How so, exactly?
Well, think about sustainably managed forests. The idea is you harvest trees, but you also replant them. So it's a continuous cycle, ensuring there's, a constant supply without depleting the resource. It's not like mining ore for steel.
And I saw something really interesting about carbon sequestration, was it?
Yes, carbon sequestration. It's a huge point. Trees, as they grow, they literally pull CO2 out of the air.
Right.
And when you use that wood to build a house, that carbon stays locked inside the wood for the life of the building.
So the house itself becomes kind of a carbon storage unit.
Exactly, a carbon sink.
Yeah.
Which is, a stark contrast to materials like concrete and steel. Their production releases a lot of carbon and uses significant energy, what we call embodied energy.
Embodied energy, meaning the energy used to make the material.
Precisely. Wood generally requires less energy to process from raw material to usable lumber compared to steel or concrete.
Yeah.
And modern techniques like prefabrication, they cut down waste significantly. Plus, any wood waste is often biodegradable.
Okay, so good for the planet. But what about, practical things like utility bills? How does wood help there?
It comes down to its natural insulating ability. Wood has this cellular structure full of tiny air pockets.
Oh, okay.
And that trapped air makes it a pretty good insulator naturally. So it helps keep your house warmer in winter and cooler in summer, which, can definitely lower heating and cooling costs.
And I gather modern building techniques boost that even further.
That's right. Especially with things like prefabricated wood elements, you can get really tight construction, excellent air tightness.
Meaning fewer drafts.
Exactly.
Right.
It seals the building envelope really well, minimizing unwanted heat loss or gain. So it really amps up the energy efficiency.
Okay, let's shift to the actual building process. Is wood faster or cheaper to build with?
Generally, yes. Wood is relatively lightweight, much lighter than steel or concrete, and it's, easier to cut and shape on site.
Right.
This often means faster construction times. And think about mass timber products like CLT cross-laminated timber.
Yeah.
These are large panels made in a factory, shipped to site, and assembled quickly. That means less labor time on site, lower labor costs, and less disruption overall.
And does that lighter weight affect the foundations?
It does significantly. Because the structure itself weighs less, you often don't need such massive or expensive foundations. That's a real plus, especially if you're building on difficult ground.
It seems really flexible, too, for design.
Huge flexibility. You can achieve all sorts of architectural styles with wood. And importantly, it's often easier to renovate or add on to a wood-framed house later compared to, say, a concrete structure.
Yeah, you said it's lightweight, but how strong is it really?
Surprisingly strong for its weight. Wood has a very high strength-to-weight ratio. Pound for pound, it holds up really well. In some cases, like how far a beam can span under its own weight, large timber can actually outperform steel.
Oh, okay, that is surprising. And what about fire? That seems like wood's biggest weakness.
You'd think so, but it's actually quite interesting, especially with large, solid timber members, like in mass timber.
How does that work?
When exposed to fire, the outside surface chars. This char layer acts like an insulator.
So it protects the inside.
Exactly. It protects the core of the wood, allowing it to maintain its structural strength for a surprisingly long time. Often longer than unprotected steel, which can lose strength rapidly when heated. It's sort of a natural fire protection.
Wow. So it holds carbon, insulates, and even protects itself from fire to some extent.
What about things like earthquakes?
Wood performs well there too. Its natural flexibility allows it to absorb seismic forces, and its lighter weight means less inertia during shaking. And, of course, if you treat it and maintain it properly, wood buildings can last for a very, very long time. And there's another aspect, maybe less obvious, the impact on people living inside. The whole biophilic design idea.
Right, biophilia are innate connection to nature. Wood is a natural material. It generally doesn't off-gas harmful VOCs like some synthetic materials can, so better indoor air quality.
Okay.
It also helps regulate indoor humidity naturally, absorbing excess moisture and releasing it when the air is dry. Plus, just having natural wood surfaces around us, studies show it can positively impact well-being, reduce stress, improve mood. It just feels good to be in a space with natural materials.
So bringing it all together with modern trends, you mentioned mass timber like CLT and glulam. That's letting architects build bigger and taller with wood now, right?
Absolutely. It's really revolutionized what's possible. Taller wood buildings, complex structures, and prefabrication plays a huge role here, ensuring precision, quality control, and minimizing waste on site.
Makes sense.
And all this ties back to the growing demand for sustainable building. Net zero energy goals, lower carbon footprints. Wood is increasingly seen as a key material to help achieve those targets. It's really having a moment.
Okay, wood sounds pretty amazing based on all that. But, and it's a big but,
Yeah.
what happens when you put a wooden house in the path of a major tornado? Or right on the coast facing hurricanes? The sources suggest this is where the story gets a lot more complex.
It really does. This is where we have to balance all those benefits we just discussed against wood's inherent vulnerabilities when facing truly extreme forces. It's a critical trade-off.
So, starting with tornadoes, what makes wood homes so vulnerable?
Well, two main things: extreme wind pressures and flying debris. Tornado winds can be incredibly powerful, exerting huge forces on walls and roofs, and the debris. We're talking tree limbs, parts of other buildings, even cars sometimes. And traditional wood framing, 2x4s with sheathing, just isn't designed to stop that kind of high-speed projectile. Penetration is a major risk. While nothing is truly tornado-proof against the most violent ones, standard wood construction is particularly susceptible.
And it's not just things hitting the house, but the wind trying to rip it apart.
Exactly. Uplift forces are immense in a tornado. The wind getting under the eaves can try to lift the entire roof off. If the connections aren't strong enough from the roof to the walls and the walls to the foundation, the whole structure can fail.
And traditional connections often aren't strong enough.
Often, no. Simple nailing isn't sufficient for those kinds of loads. Building codes have improved, especially in tornado-prone areas, demanding better connections. But it's still a major challenge for wood framing to resist the most violent tornadoes without significant upgrades.
Okay, now let's switch to the coast. Hurricanes bring wind, obviously, but also water, right? Storm surge, flooding.
Precisely. And water is wood's enemy. Heavy rain driven by hurricane winds, storm surge pushing seawater inland, general flooding, all of that can saturate wood framing.
Could even too.
Rot, mold, decay, it weakens the structure over time, sometimes very quickly, and the repairs are often extensive and incredibly expensive. Water damage is a huge issue for wood homes in coastal areas.
And the hurricane winds themselves, still a problem for wood.
Definitely. While maybe not the same extreme intensity as the worst tornadoes, sustained hurricane force winds still put enormous stress on the frame. And then there's the salt.
Ah, the salty air.
Yeah, the salt spray in coastal air is highly corrosive. It attacks metal fasteners, the nails, screws, straps, and clips holding the wood frame together. Over time, they corrode and weaken, compromising the entire structural integrity.
And building codes often require raising houses on the coast, too.
Right. Base flood elevation requirements mean you often have to elevate the house on pilings or a raised foundation. Building a structurally sound, elevated wood house that can also withstand wind and water forces adds significant complexity and cost.
So putting it all together, the sources seem to suggest that standard wood construction might not be the best default choice in these really high-risk zones.
That's a fair summary. Without significant, often costly modifications and specialized engineering, standard wood framing faces major challenges in surviving strong tornadoes and direct hurricane impacts, especially with storm surge.
But it is possible to build a more resilient wood home in these areas. It's not totally impossible.
No, not impossible, but it requires going way beyond standard practice. It involves a whole system approach, focusing on making the structure incredibly robust and resistant.
How do you do that? What kind of things are we talking about?
A key concept is the continuous load path. You need to make sure every part of the house is strongly connected to the parts next to it.
Like a chain.
Exactly. From the roof sheathing to the rafters or trusses, down the walls to the foundation and into the ground. You use things like hurricane clips, straps, anchor bolts, specialized connectors, basically beefing up every connection point so those strong wind forces can be transferred safely down to the foundation without tearing the house apart.
Okay, so stronger connections. What about keeping wind and water out?
Critical. That means impact-resistant windows and doors, think laminated glass or strong storm shutters to stop debris from breaching the house. Stronger exterior sheathing helps too.
And for water, especially on the coast.
Elevation is key, getting the living space above expected flood levels. Using pressure-treated or naturally decay-resistant wood, especially near the ground. Proper flashing, water-resistant barriers, good drainage around the foundation, and ensuring crawl spaces are well ventilated to allow drying. It's a multi-layered defense.
And the foundation itself needs to be tougher.
Absolutely. Reinforced foundations are crucial to resist both wind uplift and the scouring effects of floodwaters. Extra bracing in the walls and roof structure adds stiffness. It really boils down to using high-quality materials, paying meticulous attention to detail, strictly following or even exceeding the very demanding local building codes in these zones, and crucially, working with architects and engineers who specialize in this type of resilient design.
So it sounds like making wood resilient enough for these zones is a serious undertaking. If maybe that's too complex or costly, what are the main alternatives the sources point to? What materials are inherently better suited for, say, Tornado Alley?
Yeah, if maximizing resilience is the absolute top priority, other materials often come to the forefront. For tornado zones, the focus is really on resisting extreme wind and impact.
Like what? Steel.
Structural steel framing is definitely an option. It's very strong, ductile, meaning it can bend without breaking and handles high loads well. Metal roofing is also highly recommended, usually interlocking panels that resist uplift much better than shingles.
And concrete seems like the big one for tornadoes.
Reinforced concrete is a go-to, especially insulated concrete forms, or ICFs.
ICFs. How do they work?
Basically, they're hollow foam blocks that stack like a Lego. You put steel reinforcing bars, rebar, inside, and then fill the core with concrete.
Oh,
What you end up with is a solid steel-reinforced concrete wall sandwiched between layers of foam insulation. It's incredibly strong against both wind pressure and flying debris impacts. Some ICF systems are rated for winds well over 250 miles per hour.
wow. Any other materials mentioned?
Yeah, structural insulated panels, SIPs, can be very strong too. They're like sandwiches, rigid foam insulation glued between two structural skins, like oriented strand board. When properly engineered and connected, they create a very strong, stiff wall system. And some sources mention things like earth blocks, compressed earth, which can be very resistant due to sheer mass, though maybe less common. And of course, any safe room must meet FEMA P361 standards for maximum protection.
Okay, so those are the materials. What about the construction methods for tornado resistance? You
Yeah.
mentioned ICFs.
All right, ICFs are a key method because they create that monolithic, super strong wall. Beyond that, it's about the really robust foundations, whether it's a reinforced slab-on-grade or a pier and beam foundation with deep anchors and lots of rebar, designed specifically to resist uplift.
And the roof connection is still vital.
Absolutely critical. Even with strong walls, the roof is vulnerable. So metal roofing is preferred, ideally with a low slope or hip roof design, which is more aerodynamic. And you still need those heavy-duty connections, hurricane straps, anchor bolts, securing the roof structure firmly to those concrete or steel walls.
And windows and doors. Still a weak point.
Potentially, yes. So impact-rated windows with laminated glass and reinforced frames are essential, or strong storm shutters that can be closed before a storm hits. Preventing the windows or doors from blowing in is key to preventing catastrophic pressure changes inside the house.
And the ultimate protection.
It's still that dedicated safe room, built to FEMA specs, usually with reinforced concrete and a steel door. It's designed as a life safety shelter within the home.
Okay, now let's shift back to the hurricane coastline. We've got wind, yes, but also the huge factor of water storm surge, flooding, plus that corrosive salt air. What materials are best suited there?
Concrete and reinforced masonry, like concrete blocks filled with grout and rebar, are again top choices. They offer great strength, stability, and they just don't care about getting wet. They won't rot or mold.
Makes sense. What about steel?
Galvanized steel is excellent, especially for framing and roofing components. The galvanizing provides good protection against salt corrosion. It's strong and durable in that harsh environment.
And windows, same as for tornadoes.
Pretty much. Impact-resistant laminated glass is crucial for coastal homes too because hurricanes also throw debris. Engineered wood products like laminated veneer lumber, LVL, can be used selectively because they offer enhanced strength and stability compared to standard lumber, but you still need to protect them from moisture.
What about siding and roofing, specifically for the coast?
Durable metal roofing systems are ideal for wind and salt resistance. For siding, fiber cement is a fantastic choice. It looks like wood sometimes, but it's resistant to almost everything the coast throws at it. Warping, rotting, fire, wind, impacts, salt spray, and using synthetic roof underlayments beneath the main roofing provides a critical secondary water barrier.
Okay, so for building methods on the coast, what's number one?
Elevation, elevation, elevation. Getting that first finished floor safely above the predicted storm surge level, usually on strong piers or columns, is the most important step to mitigate flood damage.
And the foundation holding those piers up.
Needs to be deep and robust, often concrete, designed to resist the scouring effect of waves and currents, as well as wind loads. You need to anchor the house firmly against both horizontal and uplift forces.
And the connections again. Load path.
Still absolutely vital. Strong structural framing, whether concrete, steel, or heavily reinforced wood, tied together with hurricane straps, anchor bolts, shear walls, ensuring that continuous load path from roof to foundation is non-negotiable.
What about keeping water out besides elevation?
Comprehensive waterproofing is key. Sealing foundation walls, using waterproof coatings, ensuring good drainage away from the house, and really importantly, elevating all your mechanical systems, HVAC, electrical panels, water heaters, out of potential flood zones.
I saw a mention of house shape, too.
Yes, aerodynamic shapes can help. Rounded or hexagonal designs, for example, tend to experience lower wind pressures than simple square boxes. And using corrosion-resistant hardware everywhere, stainless steel or hot-dipped galvanized fasteners and connectors is essential for longevity in the salty air.
So wrapping up the alternatives, are there any general rules that apply whether you're building for tornadoes or hurricanes?
Absolutely. Number one is adhering to and honestly probably exceeding the local building codes. They exist for a reason and are usually much stricter in these high-risk areas. They represent the minimum standard for safety.
You can't just DIY this stuff, right?
Definitely not. The role of experienced professionals, architects, structural engineers who specialize in disaster-resilient design is absolutely critical. They understand the forces involved and how to design systems to resist them.
And that load path concept again.
Can't stress it enough. Making sure every single piece is tied securely to the next all the way down. It's the fundamental principle of structural integrity against wind.
And finally, you can have the best plans and materials.
But if the construction quality isn't there, it doesn't matter. Quality workmanship, attention to detail during construction, that's paramount. A well-designed house built poorly is still vulnerable.
Okay, so let's try to distill this. What does this all mean for you listening?
We've gone pretty deep into, well, the world of building materials. We looked at wood, its green credentials, its efficiency, its surprising strength, even its beauty. But we also saw its vulnerabilities, especially when faced with extreme winds and water. Right. And we saw that while you can engineer wood to be much more resilient, it takes significant effort and cost. In those highest risk zones, materials like reinforced concrete, ICFs, and steel often provide a more inherently robust solution. Understanding these differences helps you make informed choices, whether you're building, renovating, or just trying to understand the safety and longevity of your own home.
It really underscores how much our environment, the specific threats we face, should drive our decisions about how and what we build with. It challenges maybe some assumptions we have about traditional materials.
It does. And looking forward, it brings up a really interesting question for you to think about. As extreme weather events potentially become more frequent or more intense due to climate change, how is that going to continue pushing innovation in building materials and construction methods? Are we heading towards a future where resilience and adaptability become the absolute primary drivers in how we design and build our homes?
Something to definitely ponder. We hope this deep dive has given you a solid foundation, no pun intended, on this topic, and maybe spark some new questions about the structures around us. Thanks for joining us. Until next time.